Lecture 13, Liquids and Solids. Objectives. Learn some of the essential features of water. Learn about interactions among water molecules. Understand and use heat of fusion and heat of vaporization. Learn about dipole-dipole attraction, hydrogen bonding, and London dispersion forces. Understand the effect of these forces on the properties of liquids. Understand the relationship between vaporization, condensation, and vapor pressure. Learn about the various types of crystalline solids. Understand the interparticle forces in crystalline solids. Learn about how the bonding in mirrors determines metallic properties. 1. Essential features of water. Water is an unusual liquid with properties essential for life. High boiling point for its molar mass. High heat capacity. High heat of vaporization. Solid water, ice, is less dense than liquid water. These unusual properties arise from strong intermolecular forces, not from covalent bonds. 2. Interactions among water molecules. Water molecules interact through hydrogen bonding. Why water forms hydrogen bonds? Oxygen is highly electronegative. OH bonds are polar. Partial charges develop. Oxygen, delta. Hydrogen, delta. Hydrogen bonding occurs between delta hydrogen of one water molecule, delta oxygen of another molecule. These interactions create a dynamic network in liquid water. 3. Heat of fusion and heat of vaporization. Heat of fusion, delta H sub /sub. Energy required to convert a solid to a liquid at constant temperature. 4. Water.
Mayúscula delta mayúscula H subíndice fus igual a C.
Delta H of fusion is equal to 6.01 kilojoule per mole. Thus, the heat of fusion of, in this case, of water. Let's see what is the heat of vaporization.
Heat of vaporization, delta H sub vap /sub. Energy required to convert a liquid to a gas. 4. Water.
Mayúscula delta mayúscula H subíndice VAP igual.
The enthalpy of vaporization is 40.7 kilojoule per mole.
The large value of delta H sub vap /sub reflects strong hydrogen bonding. The large value of the heat of vaporization, VAP, means that a significant amount of energy is required to convert a liquid into a gas. For water, this large delta H VAP reflects strong hydrogen bonding because in liquid water, each H2O molecule participates in multiple hydrogen bonds with neighboring molecules. To vaporize water, these hydrogen bonds must be broken so molecules can escape into the gas phase. Breaking hydrogen bonds requires much more energy than overcoming weaker intermolecular forces, like dipole-dipole or London dispersion forces. Key idea. Stronger intermolecular forces implica higher mayuscula delta mayuscula H subindus VAP. Comparison example, conceptual. Water, strong H bonding, high delta H VAP, high boiling point, low vapor pressure. Nonpolar liquids, only dispersion forces, lower delta H VAP, lower boiling point. Exam takeaway, a large delta H VAP is direct evidence that strong intermolecular attractions, especially hydrogen bonding, are holding the liquid together. 4. Intermolecular forces, IMFs. Intermolecular forces are weaker than covalent bonds, but they control physical properties. 4.1 Dipole-dipole attractions occur between polar molecules. Positive end of one molecule attracts negative end of another. Moderate strength. 4.2 Hydrogen bonding. Special, strong type of dipole-dipole interaction.
Okay, you can see here that the dipole attractions are weaker than the hydrogen bonding. because these are a special strong type of dipole-dipole interactions and occur when hydrogen is bonded to nitrogen, oxygen, and or fluorine that are the three most electronegative atoms. Then the difference of electronegativity between hydrogen and every one of them is very, very high. That's why there is an attraction between the negative part of the molecule and the positive part of the other one. Then remember that the hydrogen bonding are stronger than the dipole-dipole attraction. Let's see what about the London dispersion forces.
London dispersion forces. Present in all molecules. Arise from temporary fluctuations in electron density. Strength increases with molar mass. Surface area.
Then this kind of dispersion forces are present in all the molecules just because of the oscillation of the charges, then can produce an instantaneous dipole, and this instantaneous dipole can induce a dipole on the neighboring of the element. So these forces are weaker than the other ones that we have already studied. What is important here, the effect of the intermolecular forces on liquid properties. The stronger the intermolecular forces lead to what? A higher boiling point, a decrease in the vapor pressure, an increase in the viscosity, and the surface tension also increases. Example, let's see this example.
Example. Water has a higher boiling point than H2S due to hydrogen bonding. 6. Vaporization, condensation, and vapor pressure. Vaporization. Liquid gas. Requires energy. Molecules escape from surface. Condensation. Gas liquid. Releases energy. Vapor pressure. Pressure exerted by vapor above a liquid in a closed container. At equilibrium. Rate of vaporization equal a rate of condensation. Small blue diamond liquids with strong intermolecular forces have low vapor pressure. 7. Types of crystalline solids. Crystalline solids have particles arranged in a regular repeating pattern. 7.1 Ionic solids. Ions held by electrostatic forces. High melting points. Brittle. Conduct electricity when molten or dissolved. 7.2 Molecular solids. Molecules held by intermolecular forces. Low melting points. Poor electrical conductivity. 7.3 Network covalent solids. Atoms connected by covalent bonds. Extremely hard. Very high melting points. Examples: diamond, quartz. 7.4 Metallic solids. Positive metal ions surrounded by delocalized electrons. C of electrons model. 8. Interparticle forces in crystalline solids. Solid type. Interparticle force. Ionic. Ion-ion attraction. Molecular. IMFs. Network covalent. Covalent bonds. Metallic. Electron C attraction. 9. Bonding in metals and metallic properties. The electron C model explains metallic properties. Electrons are delocalized and mobile. Explains. Electrical conductivity. Thermal conductivity. Malleability. Ductility. Reflectivity, mirrors. Why metals reflect light. Free electrons absorb and re-emit photons. Produces mirror-like surfaces. Free electrons absorb and re-emit photons because they are delocalized and mobile, not tied to any single atom. In metals, valence electrons form a sea of electrons that can move freely through the lattice. When light, photons, strikes a metal surface, these free electrons absorb the photon's energy. The electrons briefly move to higher energy states and then re-emit the energy as photons. The re-emitted photons travel outward, producing reflection. Why metals are shiny mirrors? Because many free electrons respond collectively. The light is re-emitted in an organized way, resulting in high reflectivity. Key exam connection. Property. Explained by free electrons. Electrical conductivity. Electrons move through the metal. Thermal conductivity. Energy transferred by electrons. Malleability and ductility. Ions slide while electrons hold lattice together. Reflectivity, mirrors. Absorb and re-emit photons. 10. Summary. Liquids and solids are governed by intermolecular forces. Water's properties arise from hydrogen bonding. Phase changes depend on energy transfer. Crystalline solids differ by the type of bonding. Metallic bonding explains key metal properties.
Well, that's all for this. Only I want to share something here. I'm going to add a graph from the web that is important for me. I'm going to show you a heating curve, and we are going to see the different steps. Okay, here I will copy. Let's see. Let me copy the figure. And I'm going to add here in such a way that you can see this is a heating curve. In this case, is of water at 1 atmosphere of pressure. When you begin heating the solid, the ice is at -30 Celsius degree. The ice begin absorbing energy until it arrives to 0. At this moment, the ice begins melting, and during this process, the temperature remains constant. This temperature at which the solid melts is the melting point. When all the solid is melted, then the water begins absorbing energy and going up until begins the conversion of liquid into gas. This is the part of the change that we call vaporization. And during the boiling point, during this change, the temperature remains constant, and this is what we call boiling point. After that, the gas begin absorbing energy and getting hotter and hotter and hotter. This is the process of heating a solid, increasing the temperature until it goes from solid to liquid and from liquid to gas. Well, that's all. See you in the next lecture.